Thank you so much for the really kind introduction. I'm excited to be here today. So I'm going to talk to you today really about the promise and challenges of language models in the clinical domain. So as a brief outline, to start, I want to give a primer about large language models in general domain NLP. Now, some of this first part of the talk may be a review for some of you who are familiar with transformer models. But during this part, I want to address what is transfer learning and why do we need it? What model architectures and training paradigms have driven recent advances? And what are some of the key differences between BERT, GPT-3, and other large language models? Then I want to transition to talking about the advances in the clinical domain. What are some common tasks in clinical NLP? Why is clinical data unique? And why might we need domain-specific models in this domain? And then how have large language models been used so far for clinical NLP? Then I'll transition to some of the open research questions in the clinical NLP domain. How can we avoid perpetuating societal biases when using these sort of large language models? How do we develop these models in settings with limited data or computational capacity? And then how do we leverage these large language models, especially in the clinical domain, without exposing any protected health information? So over the past 5 years, we've seen rapid advances in NLP, many of which have been featured in popular news media. For example, a model called BERT is now being used behind Google search. There are a number of articles now about models like GPT-3 being used to help write news articles, poetry. There's even a Reddit post about a kid helping GPT-3 with their homework. And GitHub has developed a tool called Copilot that leverages these large language models to help a user write code. Now, what has driven these recent successes in NLP? A key idea is this notion of transfer learning. So transfer learning involves training a model on a task and then transferring that knowledge to a new task. A related idea to transfer learning is this notion of pre-training, which is a type of transfer learning where we train on one task first and then leverage that pre-trained model for a downstream task of interest. And transfer learning has been used to great success for a while in the imaging domain, where you would train a model on a big data set like ImageNet, let's say to identify objects in an image. You transfer that model over, let's say, to a clinical domain where you might want to identify diseases from chest X-ray. Now, in the NLP domain, we're also now seeing the successes of this sort of same paradigm. The analogy here is that you train a model on large amounts of text corpuses. Let's say, given a sequence of words, you want to predict the next word in that sequence, and then you can transfer that model again to a downstream task of interest. To give an example, let's say you have electronic health record data and you want to be able to identify the adverse events that are mentioned in a patient's clinical notes. More concretely, the recent advances in NLP leverage this idea of self-supervised learning. For self-supervised learning, the pre-training task of predicting the next word in the sentence, like I mentioned previously, this is a type of self-supervised learning task because this task doesn't require any external annotated data, and instead you can construct those labels directly from the text itself. This training paradigm is really beneficial because it enables both the rapid scaling of models to new tasks, and it enables training models in settings when you have limited annotated data. Transfer learning is not a new concept in NLP. For a while now, we've trained these dense, low-dimensional representations of words that can be used for a variety of NLP tasks. These approaches are really driven by the notion that a word's meaning is given by the words that frequently appear by that word. So you can know a word by the company that it keeps. Starting in 2013, there were static word embeddings like word2vec, and these were the standard for several years. You generate a single embedding for each word in your vocabulary. Then starting in 2017 to 2018 came the era of contextualized word embeddings. And the idea here is that a word might have a different meaning depending on where it appears in the sentence. So the word bank might have a different meaning in the sentence, I withdrew money at the bank, compared to the sentence, the man was fishing by the bank. And the embeddings generated during this era were largely using LSTM models. Now, starting in 2018, we're starting to see this era of large language modeling with transformers. So what's really the difference there? These are still contextualized word embeddings, but instead of using LSTM models, we're using transformer models. And what we're doing, and this is an image here of a common paradigm where you'd first, again, pre-train a task on a self-supervised learning objective, transfer that entire model over to another task you might care about, and then fine-tune that entire model, both the model itself and then a task-specific head. And I'll go into more details about all of that shortly. Since 2018, we've seen the creation of larger and larger language models that have more parameters and are trained on more data. And the belief here is that training increasingly large language models will enable better performance and generalization to unseen tasks. So up to this point, I've mentioned language models, but I haven't really defined specifically what we mean by that. So informally, language modeling involves predicting what word comes next in a sentence. So given the sentence, I went to the grocery store to buy blank, you could imagine filling in that with multiple different words. Breads, egg, fruit are probably more likely than clothes, given that you're purchasing something at the grocery store. More formally, what do we mean by this is given a sequence of words x1, x2 through xt, you want to compute the probability distribution of the next word xt plus 1. And xt plus 1 can really be any word in the vocabulary that you define. So another key reason for the recent success in NLP is really this transition from recurrence to attention-based models. This prior paradigm in NLP involved using recurrent neural network models, which will sequentially process every word in the sequence. RNNs encode the linear order of words really well, and then that could be a useful heuristic. However, they're not as good at learning long-term relationships between words. RNNs take O of sequence length, number of steps for distant words to be able to interact. And as a result, also, there's also a lack of parallelizability with these models, where because you're doing recurrent processing, you can't process the representations for every word at once. So it's O of sequence length, unparallelizable operations for these models as well, which becomes a problem because then you can't take advantage of modern GPU architectures. Just to give a concrete example of this, let's consider you have the paragraph here, and you want your model to be able to fill in the blank again. Now, for the model to be able to successfully predict the word store here, it needs to remember the context from several sentences ago. This is really difficult, again, when the interaction distance between two words scales with the sequence length. All right, so what's the solution here? Current models now leverage a new paradigm. Instead of using recurrence, models now leverage attention. We'll go into the specifics as a review later, but the key idea is that at every layer, every word in the sentence can attend to every other word in the sequence. So in other words, the representation of each word can be directly influenced by the representation of all other words with an interaction distance of O of 1. Now, a huge benefit of this architecture is that the number of unparallelizable operations doesn't increase then with sequence length, and emphasis there on unparallelizable. You can generate the representation of each word in a given layer at the same time. So attention-based models were introduced in 2017 with the paper Attention is All You Need. This paper introduced the transformer architecture, which I mentioned previously. And the original transformer is a sequence-to-sequence based model. So the idea of sequence-to-sequence means you input a sequence and then the model produces a sequence. So as an example for NLP, a translation task where you want to input an English sentence and then output a French sentence would be an example of a sequence-to-sequence task. And the transformer model was actually originally designed for translation. Again, the benefit of this model architecture is that it's fast. There's only matrix multiplications as part of the model. So now I want to spend a little bit of time to just go briefly through this model architecture to make sure everyone's on the same page. The original transformer uses what's called an encoder-decoder architecture. the goal of the encoder is to map a sequence of symbol representations, so for instance, the words in a sentence, to a sequence of continuous representations, some hidden space. And the encoder here is bidirectional. And what we mean by that is that both the left and the right context of a word can influence that word's representation. Now, given this continuous representation of the input data, the goal of the decoder is to generate an output sequence of symbols, one element at a time. At each step, the model is autoregressive in that it uses the previously generated symbols as additional input when it's trying to generate the next one. So again, the output of the decoder is a sequence of text. As the name of the paper here implies, self-attention is used at multiple different steps throughout this model. And the use of attention is slightly different between the encoder and the decoder part of this model. Just for the purposes of today, I'm just going to focus on how self-attention is used in the encoder here. So let's go into a little bit more detail about self-attention and assume you have the sentence, when Andrew got into his car, he noticed it was out of gas. And let's focus on generating the representation for the word it. At a high level, you can think of attention as updating the representation of the word by taking a weighted average of all the other words in the sequence where the weights are learned during the training process. In other words, and here's the more technical definition that's used in the original paper, given a query, a set of keys, and a set of values, attention is an approach to compute a weighted sum of those values where the weights are determined by a score between the query and the keys. So you can think of attention here as kind of a fuzzy hash table. So to look up a value, you want to compare a query against the keys in that hash table. And each query matches those keys to varying degrees. You then return a sum of those values weighted by that query key score. So that then lets you create your representation of the word it that is informed by all of the other representations in the sentence. And just to go through this step by step now. So first you need to calculate the query key and value for every word. This essentially at the end of the day involves multiplying the representation of that word by a query matrix, a key matrix, and a value matrix, all of which are learned during this training process. Step 2 is to calculate the attention score between the query and all of the different keys. In step 3, you take the softmax to normalize over all of the attention scores. And then in step 4, you take a weighted sum of all those values, again, weighted by that attention score. So self-attention allows each word to focus on a particular part of the input sequence. But what if we want to focus on multiple places at once? The solution here is to perform self-attention multiple times in parallel and then combine the results. Different attention heads can then focus on different parts of the input sequence. So far, we've just gone through the self-attention layers of the transformer architecture and really focusing on how self-attention is used in the encoder. However, it turns out attention is not all you need for a transformer layer. There are a number of other different components of the architecture that are really important for the success. In the interest of time for this talk, I'm going to skip the details of all of these, but at a high level, the transformer architecture also includes feed-forward layers that have nonlinear activations. There's residual connections and layer normalization. And if you've noticed, the self-attention doesn't have any notion of position of a sequence, so the ordering of words. So you also need to add positional encodings to be able to encode the sequence order. These started out being kind of defined in advance, but now those position encodings are often learned during the training process. Okay, so now that we've talked about language modeling, we've talked about transformers, let's revisit this plot. All of these language models, with the exception of Elmo at the bottom there, and many that are not featured on this plot, are use transformers as their backbone for the model architecture. And there are many different kinds of language models that have been developed over the last 5 years. Papers are coming out one after another, but these models can generally be divided into 3 main categories. There's decoder-only language models, which use the classic language modeling objective that I described previously, where you're trying to, given a sequence of words, predict the next word. And these models leverage unidirectional context. So you only have access to the left context to predict the next word in sentence. Some examples of this model architecture include GPT-2, GPT-3, and some others that are developed more recently. There are also encoder-only architectures. So these architectures can use bidirectional context. So, thinking back to that diagram of the encoder, decoder, and the attention is all you need. So the bidirectional context, again, allows you to represent the left and the right context of a given word that you want to generate the representation for. Now, because you're using this bidirectional context, you can't use that classic language modeling objective, or else you'd be giving the model access to the part of the sentence that it's trying to predict. So using these models requires a reformulation of that language modeling objective. And examples of this kind of model include BERT, Roberta, and the long former. And we'll go into details, especially about BERT later on. The final class is the encoder-decoder model architecture. And the idea here is that you combine, ideally, the best of both worlds, where you've got a bidirectional encoder and then a unidirectional decoder. And these sort of models can be pre-trained either with a classic language modeling objective, or they can use other objectives. Examples like this include that transformer model architecture that we walked through earlier, as well as T5, which unfortunately we won't have time to go into detail today. So for a good chunk of this talk, I want to focus on BERT, which is one of these models, because this model has been most widely used in the clinical domain. So as the name suggests, BERT is an encoder-only model that leverages the transformer architecture. Using BERT, again, consists typically of two stages. First, you pre-train the model on a large corpus of unlabeled data, and then you fine-tune on the task of interest. So the core idea of BERT is, again, to pre-train the model on self-supervised objectives that can be derived from these large amounts of unlabeled text. So BERT has two different pre-training objectives. The first is this masked language modeling objective, in which the model learns to fill in masked words in a sentence. And then the second objective of BERT is this next sentence prediction objective. So given two sentences, you try to predict whether sentence 2 directly follows sentence 1 in the corpus. So in the example here on the slide, we'd input the sentence, I withdrew money at the mask, I bought a present with the money. We try to get BERT to learn that the masked word is actually bank, and that yes, the second sentence does follow the first sentence. Now, after you've pre-trained the model on this large amounts of unlabeled data, you can then adapt that model to a task of interest. And what you do is you take off those mass language modeling head and the next sentence prediction head, transport the rest of the model, and then you can randomly initialize a task-specific head with parameters that are unique to that task. So what I'm illustrating here is a clinical named entity recognition task, where the goal is to try to identify problems that appear in clinical text. So now that we have a high idea how BERT works, let's talk about a few of the details that will come back later. So for the masked language modeling objective that I talked about, BERT tries to predict 15% of all of the tokens in the corpus. And of that 15%, 80% of that 15 are actually masked. 10% are replaced with a random token, and in 10% of the time, you leave the word unchanged. Now, you might ask, okay, why don't you just mask all 15% there? The idea there is that you want to make sure that the model can build strong representations of the non-masked words as well. This is especially important because at fine-tuning time, you're not actually going to see any masked words. So you want the distribution between pre-training and fine-tuning to be similar. So the BERT was pre-trained on two different data sources, the books corpus, which is 800 million words, and English Wikipedia, which is about 2,500 million words. This is now actually relatively small, but circa 2018 was quite large. The architecture here, again, thinking back to that transformer model that we went through, there are two different variants of BERT. BERT base has 12 different transformer layers, and BERT large has 24 transformer layers. And here, BERT is an encoder. So if you think about that encoder-decoder diagram, it's the encoder part of that diagram that represents a single layer. And BERT base has 12 different multi-headed attention heads, and BERT large has 16. Now, it takes a really long time to pre-train these models from scratch. It's 4 days if you're using 64 TPUs. The good news is that if you want to fine tune these on a task you care about, then it can take a couple hours. And then one other thing I want to mention is the vocab. So BERT has a 30,000 token vocabulary, and what is included in the vocabulary is a CLS token, which is put at the beginning of every sentence when you input into BERT that allows you to just represent the entire sequence that you care about that it's input. Now, I mentioned BERT's vocab consists of 30,000 tokens, not 30,000 words. The reason is because the vocabulary of BERT and other language models like that consists of subwords instead of whole words. So previously, models would tokenize text into a series of words. The vocabulary would be fixed and defined by all of the words seen at train time. And then at test time, any words that weren't seen in your vocabulary would then be mapped to this unknown token. And obviously, you don't necessarily want all low frequency words to be mapped to an unknown token. So just to give an example of this, cat and tree might be in your vocabulary, but let's say there's a misspelling, you add an extra E onto tree, that would be mapped to unknown. Let's say the word penicillin wasn't in your training corpus, so that might also be mapped to the word unknown. So nowadays, what we use instead is this idea of subword tokenization. So the idea here is that you want to learn a vocabulary of common subwords that appear in your corpus. And then at train and at test time, you can break down each word into a set of subwords that appear in your corpus. And typically, every subword vocabulary consists of all of the characters in the given alphabet as well. So in a worst case scenario, you're breaking down each word into its constituent characters. But ideally, you have some subwords and not just the character level itself to tokenize the word. So going back to those examples, in this subword tokenization scheme, maybe cat and tree, the entire words are still in your subword vocabulary. But now tree with an extra E isn't, and it might be broken down into the two subwords, tree, and then the letter E. And penicillin might not be in the original subword vocabulary, but the subwords pin, I, sil, lin might be in there. So this allows you to decompose these words that aren't in your vocabulary to subwords that are. And I'll note this for later, is that the vocabulary in which you, or the corpus in which you develop your subword vocabulary will have an impact on the kinds of subwords that are there. So if you imagine a subword vocabulary trained or developed on a general domain text may not necessarily transfer well to a domain-specific text. So we just walked through the BERT model, but there are many variants of BERT, let alone many different kinds of decoder-only or encoder-decoder language models. So there are two particularly useful variants. Roberta is like BERT, but you train for longer and on more data, and you remove that next sentence prediction task. So you only do masked language modeling. There's another variant called span BERT, where instead of just masking a single token or a single word, you instead mask continuous spans of these words. And the idea here is that this makes for a harder pre-training task so that hopefully the model can learn to represent language better. So up to this point, I've really focused on general domain introduction to large language models. And now I want to transition to talking about large language models in the clinical domain. All right, so again, everything is focused thus far on general domain NLP. It's a natural question to ask, do these advances apply to the clinical domain? Now, before we answer that question, what does the clinical domain even mean? In particular, I'd like to differentiate between clinical and biomedical text. By clinical text here, I'm referring to things like the notes that your doctor will write in your electronic health record when you go to a hospital visit, Or when you're admitted to the hospital, clinicians might write an admission note or progress notes for every day you're in the hospital, or a discharge note when you're sent home from the hospital. Clinical text can also include things like patient messages or transcripts of patient-physician conversations. However, these currently at least are used to a lesser extent in the research community. In contrast, what we refer to by biomedical or scientific text is really like PubMed and journal articles more generally, as well as different health websites. So now going back to this original question, the answer is yes. Clinical NLP has many of the same challenges and tasks as general domain NLP, for which these large language models were built. So here's a few of the tasks that you might do in clinical NLP listed here. So for example, you might want to develop a question answering model that can answer questions that clinicians ask about a patient's history given their electronic health record. You might want to help a clinician answer a patient's note that they send on their online patient portal by generating a response to that question. You might want to translate the notes about a patient from English to the patient's preferred language to help that patient to better understand their hospital stay. A really big one is information extraction, where you have all this information represented in unstructured text. Can we try to convert that into a structured format? And this can either be used for a specific task, like for instance, identifying adverse events, or maybe that now structured information is used downstream in a larger model. So while there are many similarities between clinical NLP and general domain NLP, there are many unique features of clinical NLP as well that make the domain unique and suggest that maybe it will be hard to use these out of the box. So on the right here, what you're seeing is an example of a radiology report. And I'm sorry if it's a little small. So the radiology report describes the interpretation of imaging like a chest X-ray or an MRI. And as you can see in the radiology report, there are many medical abbreviations and incomplete sentences. There's templated text. So you can see kind of the template here: indication, comparison, findings, impression. And that template can vary by specialty and it can vary by clinician. The text is often semi-structured and into like lists and tables. These notes often contain copy and pasted information. Clinicians are tired, they copy information from the prior note into the current note. And because many of these tasks require a lot of domain expertise, annotating data in this domain can be really challenging. And then finally, as data contains protected health information about a patient and any medical condition that they have, so it can be really difficult to share the data and the models that are generated on that data due to these privacy concerns. So in light of the differences between general domain text and these specialized domains, many domain-specific language models have been developed. One of the first domain-specific models was BioBERT, which was created for the biomedical domain. So BioBERT took a pre-trained BERT model and then continued to pre-train that model on the next sentence prediction and mass language modeling objectives using data from PubMed and PubMed Central. And they found that when you continue to pre-train on this domain, you can get better performance on downstream biomedical tasks. Now, as I mentioned, clinical text is even different than biomedical text. So some colleagues at MIT created clinical BERT. So here what we do is we start with BioBERT and then continue to train that model on text from Mimic3. So Mimic3 is really one of the only available notes databases to the research community. So it consists of notes from the intensive care unit, or ICU, from Beth Israel across the street. And it's really the primary data set that many people in the research community use. So what we did is we initialized the weights of the BERT model with BioBERT, and then continued, again, pre-training on those two pre-training objectives using notes from either all of the notes in Mimic3 or only the discharge summaries that are found in Mimic3. And if you'll note here, The size of the Mimic3 corpus is much smaller than both the PubMed and the general domain corpus. And this was really a motivation for why we decided to continually pre-train these models instead of training from scratch. There's simply just not enough publicly available with a DUA data to be able to train these from scratch so far. So because both of these models were initialized with the original BERT model, the downside is that you're limited to that original BERT vocabulary. And as I alluded to earlier, the BERT vocabulary may not be ideal for clinical text or biomedical text. I'm going to skip the details about how these models were specifically evaluated on downstream tasks, but I do want to just show you this to provide intuition. So after training BERT on clinical text, we find that the word representations it learns are better adapted to the clinical domain. So to investigate this, what we did was look at the nearest neighbor words for both clinical and generic words from the BERT vocabulary. So for example, let's take the word discharge here. The nearest neighbors for discharge for the BioBERT model trained on PubMed don't necessarily make a lot of sense, like emission, wave, light. But you can tell that the nearest neighbor words for clinical BERT are all related to being discharged or transferred from the hospital. So just to give you a high level sense of kind of what we're learning here with these different domain specific models. Now, the two models I just described are examples of continual pre-training. Again, you initialize with BERT, continue to train on a domain of interest. However, as I briefly alluded to, continual pre-training does have some downsides. So for one, the BERT subword vocabulary that was developed may not apply to this domain. So it'd be great if the word nephropathy was directly found in our vocabulary, but subword tokenization using BERT actually splits this up into 4 subwords. So nephropathy. And as a result, these models are forced to divert parameterization and training bandwidth to model these terms using these fragmented subwords. You know, it's certainly better than an unknown token, but it requires the model to do more work to model these. The second potential issue is that continual pre-training may not be able to undo suboptimal initialization from general domain pre-training. So the idea is that maybe you get into some local minimum and it's hard to get out of that. Now, as a result of these issues, this model called PubMed BERT was created. So this is a model trained on biomedical text from scratch using a PubMed vocabulary. So as a result of using the specific PubMed vocabulary, you now have words like nephropathy, lymphoma, lidocaine, et cetera, that are now present as whole words in your vocabulary. And we're able to do this on biomedical text because there's sufficient PubMed data available to train these sort of models from scratch. So PubMed was trained on biomedical text. The emphasis here is the clinical domain. What about the clinical domain? So researchers from NYU investigated the utility of training BERT models from scratch using only clinical data. So they train a clinical BERT model on 7.5 million notes from NYU. Again, they can use a clinical vocabulary here because they're training from scratch. They found that the BERT vocabulary contains an average of 49.2 out of vocab words per note, compared with 0.93 out of vocab words when they use their own clinical vocabulary. And they evaluate these models that are trained from scratch on this task of ICD-10 classification. So ICD-10 is basically an ontology that you can use to describe procedures or diseases that are associated with a visit. It's often used for billing. So I'm just going to show you a table here of results, and I really just want to focus on these 2 lines here, where they're complaining clinical BERT that was trained on ICU data, general domain, to the model that they train that's of the same size on their in-domain vocabulary. They do find that there's a significant difference between, and their model performs better than clinical BERT, but I'll leave it to the reader in terms of whether the difference in performance on this task is practically meaningful or not. I think it'll really be task specific. So I've been focusing on BERT models now out of all the other language models, just because they've been the most widely used thus far in the clinical domain. In the past few years, there have been many papers that have leveraged BERT models for a variety of tasks. like predicting readmission to hospitals, predicting COVID mortality, identifying or de-identifying, electronic health record notes, among many other applications. And if we have time later, I do want to talk about several works this year that have started using other large language models like GPT-3 for clinical applications as well. So all of the applications I showed on the prior slide used BERT, but BERT has an important limitation. BERT models can only represent input sequences up to 512 tokens, but clinical notes are often much longer than that. Now, why 512 tokens? The issue here is that self-attention is a really memory-intensive operation because each token in the sequence is attending to every other token in that sequence. That means the memory requirements grow quadratically with the sequence length. Now, there are a few solutions to this issue. The first solution that's been used with BERT models is to just, let's say we want to split the note into different chunks or subsequences. We'll make predictions on each subsequence, and then we'll somehow aggregate those predictions. And this was done in a paper that tried to use clinical BERT for predicting readmission. And what I'm showing you here is the equation that they used to try to combine the predictions on each of those chunks. I'm not going to go into the details of the equation, but you can imagine that there's a trade-off between just taking the max probability of all sequences in your note versus taking the average probability of some class from all subsequences. Now, the other solution is, okay, let's just use a different transformer that has a sparse attention mechanism that allows us to model longer contexts. One example of this approach is the long-former model. The idea here is to replace the standard self-attention with a self-attention model that scales linearly with sequence length. So instead of using BERT, the long-form is actually based on Roberta. You could substitute with BERT as well. But if you recall, Roberta is essentially BERT trained for more data for longer without the next sentence prediction objective. So using this efficient attention mechanism, the long-former is able to model sequences up to 4,096 tokens, which is 8 times longer than the original BERT model. So instead of performing full self-attention, as shown in this diagram here, the long-former model uses 3 different kinds of sparse attention: sliding window attention, dilated sliding window attention, and then a global attention. So just to go through these one by one, what do we mean by sliding window attention? The idea is that you have some fixed window size W, and each input token attends to the 1/2 W on either side of the word that it's trying to generate a representation of. The nice thing about this here is the computational complexity of this is now O of n times W instead of O of n squared. And then the receptive field at the top is then L times W. You can also, let's say you want to be able to represent even longer context, use this notion of dilated sliding window. So that's just like a sliding window attention, but instead you have gaps of size dilation D. So this means that your receptive field then can be L times D times W. So the number of layers times the dilation size times the width of the sliding window. And then finally, long-former uses global attention. So the idea here is that in some task-specific locations, you want to actually maintain full attention over a given token. So you might pick a few tokens in your sequence, and you say, for those few tokens, I want that token to attend every other word in the sequence, and I want every other word in the sequence to be able to attend to that token. And these can be task-specific, where if you imagine a question answering module, a question answering task, you might want all of the question words to have global attention, but use the sort of sliding window attention for the answer part of the task. So in a similar approach to clinical BERT, researchers at Northwestern developed a clinical long-former model by really further pre-training the long-former on clinical notes from that same publicly available with the DUA MIMIC3 database. So in their paper, they showed improved performance compared to clinical BERT across a number of different clinical NLP tasks, including classification, question answering, and named entity recognition. I'm not going to go into the details of all of the evaluation here, but this is just one example of the plots from their paper, the performance on document classification and inference tasks. And they're showing that clinical long former on these kind of tasks can outperform. So in order of performance, you go from BERT to BioBERT to clinical BERT to clinical long former. All right, so now we've talked about how large language models have really been used thus far in the clinical domain. So in the remaining time, I really want to talk about some open research questions in the field. At this point, we've covered everything you need to know for the prior talk. So this is kind of bonus extra content that I think we'll talk about, where we're really going in the future. So a key challenge of leveraging these large language models is that they have the potential ability to perpetuate societal biases that are found in the training data. This naturally leads to the question, to what extent are these biases found in these clinical language models? And then, the real important question is, can we design approaches for mitigating biases while maintaining high performance on these models? So there are many different ways that bias can be incorporated into machine learning models, both through the data generation and the model building and implementation process. But when we talk about bias in language models, we're often focusing on these first two sources of bias here, historical bias, and then to a lesser extent, representation bias. So historical bias arises even if the data is perfectly measured and sampled, if the world as it is or was leads to a model that's poor outcomes for that population. And representation bias here often occurs when the data that you're training the model on underrepresents some portion of the population. So one major concern with leveraging, again, these large pre-trained language models is that the models will capture and perpetuate any of the societal biases. There have been several papers that have shown that this is true for general domain NLP, but until recently, it was unclear, what this looks like in the clinical domain. So to give an example, researchers at Toronto and MIT gave the following prompt to SciBERT. SciBERT is another variant of a BERT-based model. Here it's trained from scratch on PubMed and computer science articles. And they give the prompt, patient became belligerent and violent, sent to blank. And then they ask the models to fill in that blank. And it turns out when you replace the race with Caucasian, the model fills in hospital, but when you replace the race with African-American or African, it fills in prison. Now, that was with SciBERT, that sort of proof of concept experiment. I did a quick investigation of that same prompt using clinical BERT. And the good news is that clinical BERT doesn't complete it in the same way as that SciBERT model did in that prior paper. So for all races, it completes the sentence, patient became belligerent and violent, sent to floor for every single race. So floor here is like the hospital floor. However, I asked the clinical BERT to fill in the mask for this phrase, 83-year-old, insert race, insert gender with a history of mask. And you find that clinical BERT will output very different things for that mask, depending on whether the patient is a man or a woman, or whether the patient, or whether the text indicates that they're African American or not. Now, one thing I do want to make sure to mention is that, especially for clinical texts here, it's not necessarily the case that you would expect the same condition for every single race or every single age, because there are genetic reasons why there might be between different populations. But the issue comes when the training data is underrepresenting a given population, or when it just doesn't, or when the data itself that we know is biased. So for instance, if you're training a model on data where women are underdiagnosed with heart attacks, then you're likely to perpetuate that into the model that you train it on. And you can experiment this with yourself if you go to the Hugging Face Model Hub. So we're almost out of time here, so I'm just going to talk high level about these last two topics. But at this point, we've really been focusing on this paradigm of pre-training and then fine-tuning that whole model on a target task. And the challenge is that this paradigm can still require non-trivial amounts of labeled data. So this raises the question, can we leverage models that operate in 0 or few-shot settings for clinical tasks? And can we develop pre-training objectives that better align with the downstream task of interest to try to avoid, the continual fine-tuning? And I'm going to skip these slides here, but I do want to say that Monica, who's in the audience here, has done some really cool work in looking to see whether we can use GPT-3 for clinical tasks in a 0 or few-shot setting, even when we're not, continuing to pre-train GPT-3 on clinical data. So I would encourage you to check out her paper, Large Language Models are 0-shot clinical information extractors. All right, we'll skip. So the last topic I wanted to talk about was related to privacy. So training large language models on sensitive data has the potential to expose protected health information. So this raises the question, to what extent do different large language models expose sensitive data, and can we design techniques to minimize such risks? So there's a paper that was done a couple years ago that looks at whether BERT can reveal protected health information. And they asked the question, can BERT models uncover patient condition relationships? And can you even just identify if a model has seen a patient name during training? So they train BERT models on EHR notes where they've reinserted patient names into the notes, and then they have these series of 3 different ways that they try to extract information from that pre-trained BERT model. I'm going to skip the details here, but the conclusion really is that it is actually pretty difficult to extract this information from BERT models. The same cannot be said for those decoder-only models like GPT-3. And there have been other papers not in the clinical domain that show that you can reveal sensitive information like email addresses from like GPT-2. So I think, it's still an open question to what extent you can share these sort of things across, for instance, institutions or publicly. All right, so that was just a few of the open research questions in the area. There's really a lot more, and I'm happy to talk about those during the Q&A. I just want to leave you with, how can you actually leverage large language models? So there's this website called Hugging Face that has this huge model hub. If you search clinical in the model hub, you can find 192 different clinical-based large language models. So very active research area right now. If you click on any single one of them, it will pull up a model card that talks about how each of the models are pre-trained and how you can use them. And then, of course, I didn't talk a lot about GPT-3 today, but you could also use GPT-3's OpenAI API. The downside here with clinical data is that many of these clinical data don't allow you to actually post the clinical data on the API. And so there's an alternative. Facebook released this open pre-trained transformer model, which allows you to use that model locally. So that was a whirlwind. Thank you so much, and happy to open it up to any questions.
If there are any live audience questions, please come down to the microphone. And if there are any questions on Zoom, please just unmute yourself and ask.
Just to get the ball rolling, I would love to hear your thoughts, Emily, on this issue we've seen with language models of prompt engineering, where slightly different changes to the prompt or the phrase that you give to the language model can lead to very different outcomes, and especially how that applies in the clinical context where, we want to give kind of well-calibrated and robust answers because the risk is so high in this domain.
Yeah, it's a great question.
Any thoughts?
Yeah, so I will say that I think we're just now starting to see these kind of prompt engineering type papers in the clinical domain. It's really been focused on the like BERT pre-training fine-tuning paradigm. But there was a paper released this past year about using both static prompts, but also kind of instead of assuming that you have some sort of static prompt that you're going to feed into GPT-3, you can instead try to fine tune the prompts themselves. So instead of passing in like a string of text, you say, you know, I'm going to make this some soft differentiable embedding that I can learn. And then instead of having to fine tune an entire model, you can fine tune these prompts instead. And I think those might be, you know, a reasonable intermediary, especially for like a safety critical domain like healthcare.
Hi, Emily. Thanks for the nice talk. Is there a way to, it's kind of it's really interesting because you're just kind of looking at all these words and trying to make these predictions, but there's obviously this huge medical corpus, like it's very structured. Like we know results of clinical trials, we know disease occurrence across demographics and age groups. Is there a way to like more like other machine learning models that you would imagine kind of representing that more like as a very strongly weighted thing rather than just random like African-American women, breast cancer, it figures it out, like actually like really encoding facts that we kind of know about disease and intersecting that with these transformer models to kind of remove some of these like wonky predictions?
Yeah, that's a great question. So I think there is an emerging field here in terms of how can you use both NLP methods with methods that use knowledge graphs. So clinical data and biomedical data is actually really rich in structured data in the form of knowledge graphs where you have information about diseases to symptoms, even, you know, genes associated with those symptoms. So there's something called the UMLS, Unified Medical Language, forgetting what S stands for, system. But knowledge graphs like that, I think, are starting to be integrated into these sort of models. The simplest way that people do it is that they try to identify terms that are found in clinical text, and then you can essentially concatenate the knowledge graph embedding associated with that term with the actual text embedding. I suspect there will be, you know, better perhaps ways to integrate those throughout the model process. There's also, you know, I mentioned, I focus on text data here in the electronic health record, but there's a ton of structured data about your electronic health record, like the medications, the procedures that you undergo. And I've also seen some works that are trying to do this sort of multimodal representation learning, where you try to say, how do I relate the representation of the medication in the structured form to the way that the medication is mentioned in the text data as another way to kind of enforce that? Great question.
Hi, thanks for the nice talk. Have you thought, is there any work on multilingual birds in the clinical trial data or clinical data domain or clinical domains?
Yeah, that's a great question. So is there any multilingual work in the clinical domain? You know, there are some, obviously a lot of the focus is on English. There are some clinical data sets that exist in Spanish. So I think in particular, there's like a radiology report data set in Spanish, but honestly, at least I'm not aware of any that really try to do translation on clinical text in particular. I do think that's a really interesting area. And, you know, now I'm working at the Brigham, really trying to focus on these problems that are important to the hospital. And that's something that folks at the Brigham have expressed interest in is, you know, can we try to do this translation? Because there's really a big equity, you know, question there of can you make this medical data accessible to patients of different populations?
Great, thanks so much, Sam, and thanks again to Emily for a really awesome primer. Really set the stage well for what Pulkit and I will be talking about. So today we will be talking about using electronic health record data to do some of the things like Sam mentioned, downstream risk prediction, disease modeling, even looking into the genetic underpinnings of disease. I'll start out with our group, Machine Learning for Health's general strategy and approach to research, talk about the data that we've collected and how we plan to use that data, and then some of the challenges that we've discovered when trying to work with these data, and a natural language processing framework that Pulkit and I and our group have developed to help alleviate some of these problems that we've discovered. Doesn't seem to be working. So just as an overview of our scientific goals as a group, we're very much interested in biological discovery, finding new mechanistic disease pathways, and investigating the genetic architectures that underlie disease. We'd like to be able to find ways to predict disease risk more effectively, which patients will get sick, which treatments are appropriate for which patients. And to the degree that we can use relatively low cost or non-invasive diagnostics such as electrocardiograms to predict the kinds of things that more invasive procedures would normally be used, the better. And we have various strategies for attempting to do that. And ultimately, we'd like to help develop new therapeutics, find new drug targets, or find ways of enriching clinical trials for individuals who are more likely to develop a particular outcome of interest. And most of our work is based on what we call the deep phenotype hypothesis. So many phenotypes are commonly used in clinical research. The classic example is the body mass index. We hypothesize that more traditional phenotypes like this are relatively crude or kind of low resolution. They work reasonably well at a population level, but there are many issues when one tries to apply something like, essentially a ratio of weight and height for a particular individual, because this sort of glosses over a lot of important information kind of inside the individual. Often doesn't generalize well across different subgroups of the population and so forth. So what we found in a really nice piece of work from some people in our group, including Marcus Clarkfist and Saket Agarwal, is that if you look at a whole body MRI, such as you can see here, there are ways of quantifying specific subtypes of adipose tissue, which more precise quantifications of specific subtypes of tissue turn out to be more effective for understanding sort of things like type 2 diabetes risk, as well as the genetics underlying these more informative phenotypes. And our argument, the reason we call these deep phenotypes, is that quantifying things like subtypes of adipose tissue is very time consuming and laborious for the human to do, even an expert. But using deep learning methods, we are able to scale this approach in order to actually be able to use large quantities of this type of data to do downstream modeling. And this is just to say a large part of our strategy is working with a large group of both clinical researchers and machine learning practitioners. Many of us here at the Broad, including our core machine learning team in the data science platform, as well as clinical experts at many of the hospitals in the area. And I'm learning, but I'm not a clinician or clinical researcher in my background, but as a way of setting the stage for the work that we do, one can think of clinical observational studies as being broken down into two general categories. One can design a prospective study, the defining feature being that the study itself is conceptualized and designed before any outcomes develop in the individuals included in the study. And then once the study is designed, one identifies a study population, determines what types of features one would like to collect over time, and then collects those data in a sort of a specified way into the future. And this is how many clinical trials are done, for example, and it's an effective way to do research. However, it can be quite time consuming. One has to wait potentially a long time for outcomes to develop, and it can be quite expensive just because it takes so much time and expertise of the individuals involved for collecting these data. An alternative approach is to take a retrospective approach in which the study is conceived and designed potentially after outcomes of interest have developed in individuals. And this obviously sort of requires, once the study has been designed, going back in time and collecting data relevant for the study in various ways, including from the electronic health record, which we'll talk about in our talk. And Emily mentioned the benefit of this is one can potentially collect orders of magnitude more data than one would normally do in a prospective study. This is relatively non-expensive. It can be difficult to access these data, but we're fortunate to work with researchers who are able to provide us with large amounts of health record data. The downside is that, and we'll dig into this pretty deeply, these data were not collected for research purposes in the first place. It's very inconsistent which types of data have been collected for various individuals, and we encounter significant missingness and difficulty in sort of precisely defining the outcomes of interest. So the questions that motivate our work, first of all, is what data do we collect in order to do our research? How do we extract the actual information from this data that we would like to use for downstream analyses and modeling? We're, as I mentioned, fortunate to work with expert clinicians, but their time is extremely valuable and limited. So how do we optimize their efforts? And as Emily hinted at, how can we use natural language processing potentially to help optimize these efforts? To address the question of what data do we collect, we collectively, but initially conceived by Sean Kershid with Dr. Steve Lubitz, the idea of the Community Care Cohort Project, which we refer to as C3PO, and we like to use Star Wars acronyms, I guess because we're a little nerdy, but I'll talk about what this cohort consists of and what data are included, and also a little bit about our JEDI extractive data infrastructure, which is what we collectively refer to the data extraction and analysis pipelines that we've developed. So what is C3PO? Generally speaking, C3PO is designed to be a large general purpose cohort of data from individuals who use the Mass General Brigham healthcare system for their in-network primary care. And so more specifically, we identified all individuals who sought primary care at MGB at least twice with at least a 1-year gap between 2 visits. The idea being these individuals are more likely to have more longitudinal follow-up data and not for a specific healthcare concern or disease, but just sort of seeking general healthcare. These data were last collected in the summer of 2019, but these data go back even into the early 90s. And then we've attempted to collect basically as much data as we can for these individuals from the EHR, including structured data such as diagnostic codes and lab values, free text notes and semi-structured reports, which we'll talk about in a moment, as well as various forms of imaging data, ECGs, MRIs, CTs, echocardiograms, et cetera. So a lot of data, super rich with information. And to give you a sense of the scale of the data that we're working with, over 1 billion pieces of structured data, over 100 million documents, including notes like discharge summaries and reports such as radiology reports, and some associated genotype data, which is growing over the next few years, which is exciting. And I won't go into too much detail in terms of these numbers, just to say that we have a lot of data of different types for a lot of different people, both before and after follow-up as defined by that second primary care visit. And just as a kind of a sanity check to show that these data are useful for our purposes, we took both C3PO and what we call a convenience sample, meaning looking at all individuals who have data at MGB, not just the C3PO cohort, who have all of the features for this standard risk score for atrial fibrillation. And when you apply this, calculate this risk score for all of these individuals, we showed that the score is much better calibrated for C3PO than the convenience sample. And you can see kind of by that early bump in the convenience sample, indicating that the convenience sample is probably over-enriched for people who are kind of closer to developing atrial fibrillation than the general population. And so between the two cohorts, the score is comparably discriminative. So this gave us confidence that things like risk scores that we develop using through C3PO would be more effective in application to the general population, which is our goal. So that was all great, but when we started digging into the data that we had collected for C3PO, we identified at least two significant general types of problems. One being that even for what one would think very common measurements such as height, weight, blood pressure, there's a really substantial amount of missingness, which drastically limits the amount of C3PO that we can utilize, which is unfortunate. We also found that our group works primarily in the cardiovascular disease space. A common outcome of this type is heart failure, obviously a significant problem for the global population. If our goal was to identify the hospitalizations for any patients in which a incident heart failure diagnosis had been made, the common approach to doing this in these types of studies is to use diagnostic codes. The problem is, as Emily mentioned, these codes are not primarily designed for research purposes, but generally billing purposes, and so may be assigned to patients who, for example, have had a heart failure diagnosis in the past or are demonstrating signs of heart failure, but don't meet all the criteria for an actual heart failure diagnosis. And so upon clinician review of several hundred examples of heart failure code associated hospitalizations, almost 2/3 of these encounters or hospitalizations were not actually valid incident heart failure diagnoses. And so these problems collectively were very limiting in terms of our ability to use these data for downstream research. So we had the idea that a lot of the information that we're looking for is contained in the text that we've collected, both measurements in sort of unstructured and semi-structured form, where things like height, weight, and other measurements are just listed in these documents. And often in documents such as discharge summaries, the clinician will write information about the diagnosis made in that encounter, which may more accurately reflect what actually happened in that encounter than the diagnostic codes associated with the encounter. And so that kind of was the seed for this idea that perhaps we can use some of the natural language processing methods that Emily mentioned to extract this information to make our data more useful. And I'll hand it over to Pulkit to talk about our data.
Thank you. So let's get into the clinical text that's actually contained in C3PO. We have 113 million notes, just to give you a scale. And here I'm showing the different counts by note type with a total of 71 billion words. So the good news is we have a lot of data and we have to figure out how to use it. And also things get messy, right? Like data capture in an EHR system is not perfect. And so I'm showing here the counts of notes again by type, but over calendar year. And you see sometimes they just disappear, right? Like in this LNO thing here, in this light pink in the middle, things were fine and there's lots of notes until 2015, and then suddenly there's no notes anymore. And turns out the hospital system changes how notes are captured. And so now that note type is divided into 3 other note types that are in green and purple across the different rows. So we have to be really careful where this data lives, what's in it, and how we access what we want to access. And on top of that, clinical text is complicated. So on the left here, I'm showing an illustration of a discharge summary. And there's a bunch of things that happen. When you go from PDFs to plain text, you get a bunch of junk characters. There's a lot of auto-generated content and copied measurements. And maybe the useful narrative information that's actually written by a clinician is concentrated in small segments of this really long report. And on the right, I'm showing cardiac MRI reports, and there's information about technique, machine, the actual measurements, a whole bunch of things. So these are both examples that I'm going to talk more about, but as you can see, things are not as easy as there's a few sentences and we can easily get the information that we need. So as Emily extensively covered, there's been an NLP revolution happening outside of clinical science for some years now. I won't get too much into this because she's done such a good job. But that leaves us with many questions about clinical NLP, right? So we have these really effective large language models. Can we apply them to clinical text? And so there's a bunch of open questions. What model types work best? Encoder only, decoder only, in what contexts? How do we trust that when we use these models, they're working? Because potentially the stakes are pretty high. And then do we need to train or pre-train our own models? And finally, will one model work for everything, or do we perhaps need to vary all of these questions by task? So these are pretty large open questions, I would say, and our talk cannot address all of them, but hopefully we'll get into some of the work that we've done addressing some of these questions, and then you'll have a better sense from what we've seen. So the first, I'm going to present 2 vignettes of research projects that we've done in the ML for Age collaboration to sort of show you what we've built and what we've learned. And the first one is identifying heart failure hospitalizations from discharge summaries. And the clinical lead on this is John Cunningham, who is an incredible trooper and has been an amazing partner in doing all of this NLP work and labeling a bunch of discharge summaries, more than anyone should really have to look at. So heart failure is the 3rd leading cause of hospitalization in the US. And so we care about the biology. It's a great burden on individuals and on the healthcare system. And it's hard with codes. So here on the right, you're seeing what billing codes look like. So they're sort of these diagnostic codes are associated in structured form with the different hospitalizations that we have in the EHR. But then when you go in and actually look at the hospitalizations, only 1/3 of them actually meet heart failure diagnostic criteria. Like Chris explained, so we need to do better, right? Like you can't have a 1/3 shot of having your outcome labeled if you want to answer biological questions. So we think we can do that with discharge summaries. So as I mentioned, discharge summaries contain all the information we need, but there's a bunch of caveats, and so we need to figure out how to get what we need. And so in addition to there being some documents having useful information, one other problem is that in this discharge file, we sometimes match things that are just completely irrelevant. So it could be discharge orders of this person is ready to be let go, or instructions about taking your medication and calling your doctor. So since we're working in a real world messy setting, our first step is identifying the relevant information that we want to give the model. So here I'm just going to walk you through like what the big picture workflow is for this project. So we start with hospitalizations that have heart failure billing codes. And I forgot to mention that even though these aren't very specific, they are very, very sensitive. So it's really unlikely that you're going to have heart failure and not have a code. So the problem is we have this big set with codes and we just want to filter them to the ones that are true. So it's cool. We can use the structured data as a starting point and then refine it from there. And then step one is identifying informative discharge summaries, which is a pain. In an ideal world, we wish we just had a piece of structured information that tells us what the right document is. But the good news is we can use the same method to identify informative discharge summaries that we do to identify diagnoses like heart failure. So with that sort of spoiler, I can get into the actual methods that we're using here. Emily explained super extensively a lot of these models these transformer-based models that we're working with. So bio discharge summary BERT is Emily and Co's model, PubMed BERT, SAP BERT, these are all clinical and biomedically trained BERT-based models. So they have an attention window of about 512 tokens. And then we have the standard BERT-based model, which is, I might have switched these around, pretend that these are in the correct order. I think you see that. So basically we have BERT models that are 512 tokens long and long form models that are 4,096 tokens long. So that's basically the number of tokens that they can look at. And then we have clinically pre-trained or not. And I think really what our contribution here is we've been able to build a flexible and general pipeline where we're able to quickly iterate and switch out these models and apply them to real world clinical data. And we're able to do that by using Hugging Face, which Emily mentioned, and also JEDI, which is sort of our team's data infrastructure pipeline, as if we didn't have enough Star Wars initialisms. So Hugging Face is a library of transformer functionality, but it also has this associated model zoo. And here on the right, you're seeing a screenshot of all the different model weights that are available. So this is really exciting that we're able to share pre-trained models within the research community, and that I think really accelerates progress. And then our challenge was, how do we deploy these behind the partner's firewall? Because all of this information, all of this data has protected health information, and we can't put it on a publicly hosted API. So it has to work within the Mass General Brigham healthcare system and behind the firewall with the compute constraints that come with that. So now I can get into how we actually went about doing this. We started out with having John, who's, again, such a trooper for labeling so many reports, just go in and say, yes, this document is informative, and no, it's not, for every document associated with a hospitalization. And we did this for 100 hospitalizations. It's bad, but it's not too bad. And you see here on the right in green, the distribution of the number of like true informative discharge summaries associated with each hospitalization. So sometimes, like 11% of the time, there's just no useful information in the EHR. That's the 0 bar right at the beginning, which means none of the documents that we found in the EHR are really informative, which is unfortunate, but also speaks to the difficulty of the task. And then like 80% of the time, there's only one, which is great. And then there's sort of a tail for having additional informative discharge documents. And this has to do with like hospital or time error, a whole bunch of stuff. But now we actually have some examples of like what's important and what's not. And we can train a transformer-based model on these labels and then hopefully apply that to the whole cohort. And that's exactly what we do. So here is a bit of a spoiler. Clinical long former works the best because it has both clinical pre-training and a longer attention window, so it can read more of the note. And in fact, we just divided the train and test set into 50 hospitalizations each. And that's sufficient to get us, honestly, pretty good performance. So on the left here, you're seeing a precision recall curve with an average precision of 0.97. And on the right, the AUROC is 0.985. And we are able to select this threshold there where both the precision and recall of this model is about 0.96. So the model can mostly tell when an input is informative, and that's really useful and lucky for us. And so we're able to apply this model to all of the discharge summaries that we have in C3PO, and then we're finally ready to talk about heart failure. Awesome. So step 2 is expert cardiologists adjudicate heart failure. And turns out this also isn't as simple as you would expect. So we actually do 2 stages of adjudication. The first one is discharge summary review. So that's the same thing that we've been talking about all along. There are these text documents that have discharge information, and John looks at them, says, yes, this is an inpatient hospitalization, incident inpatient hospitalization or no, and then we can do model development there. I will say this is not an easy task. You need 1 symptom, 2 signs, and at least 1 treatment to say like incident diagnosis. And even expert cardiologists will disagree when they're looking at the full chart. And that's precisely why we have an other mode of adjudication, which is full chart review. So it turns out that the full EHR chart, when you go into Epic and look at it, has a lot more information than just this discharge summary document. And so to make sure that our model is actually working, we have some hospitalizations where the cardiologist went in and looked not only at the discharge summary, but also at all of the other information available in the EHR to make their decision. So this is like a more gold standard expert label, and we use this for clinical validation. So we set this up as a clinical study, and we're able to do this principally. So just to summarize, the model only ever sees discharge summaries, and it's trained on labels from a cardiologist that only saw discharge summaries. But at the end, for final validation, we evaluate it on labels derived from the full chart EHR. Does that make sense? Awesome. Cool. So that's kind of the setup of this, and let's see how we do. So here I'm comparing general versus clinical pre-training, and then attention windows, the length of attention windows for each of these models. And what we see is all of the models do relatively well. So it's nice that we're seeing some consistency, but clinical long former outperforms the BERT-based model, the clinically pre-trained BERT-based models by quite a lot. So we get a 0.89 average precision and a 0.93 AUROC. Whereas the clinical BERT models are sort of in like the mid 70s for average precision and the mid 80s for AUROC. And then for not clinical pre-training, interestingly, BERT-based, which is not clinically pre-trained, it's just book corpus and Wikipedia, also is in the same range. And then long former, there's some boost, and it like marginally outperforms the clinically pre-trained BERT models with its longer attention window, but clinical long former still kind of wins. And I think what this is telling us is really the utility of both of those things. The combination of clinical pre-training and a longer attention window in practical terms really, really helps with performance. And we can also see that clinically pre-trained models learn with fewer labels. So that's a real advantage as well. On the x-axis here, you're seeing number of training examples in the training set. And then I'm just showing average precision on the test set on the y-axis. The test set is always the same. And the different colors are the different architectures. So maybe to start out with, we have clinical long former in green, which shoots up and then stays up throughout the subset analysis. And we see long former is maybe a bit fussy. It has like a smaller batch size to fit it into a single GPU in memory. So maybe it kind of got stuck in a local minima. So you see this little like dip here, which isn't ideal. But it does sort of starts slow, but it catches up with the smaller clinically pre-trained BERT models. And then if you compare the blue line to the red, yellow, and brown lines, again, BERT base starts out with lower performance in the blue line, but then kind of catches up. So if you give non-clinically pre-trained models more data, they'll eventually be able to learn. But if you have clinical pre-training, then they learn faster, which that's good. We would hope that, because that's kind of the point of clinical pre-training. And this is important because now the number of labels you have is often the rate limiting factor, because expert time is limited and you don't want to waste some clinicians' expert time labeling more data than you actually would need, where all of these run in a very reasonable amount of time. So long former models on our infrastructure take a couple of hours and the BERT models take a couple of minutes. So that's really helpful. Great. So here I'm just showing precision and recall curves and ROC curves for our final selected model, which is clinical long former. The average precision is 0.89 and the AURC is 0.93, as I said. And these little dots here are more refined structure definitions, just to give structure data the best shot that it possibly can have. So some folks use primary heart failure code as the structure diagnosis. So the billing codes can have primary or secondary designations. And if you filter by that, you get slightly better precision of 0.58 rather than 0.36. But you can see that our NLP model quite decisively outperforms all of the structured measurements that we could find. Great. Okay, so this is the test set. And now we're going to move on to the validation set. So just as a reminder, test set was labels derived from discharge summaries, and the validation set is labels derived from the full EHR. So it's a much harder task. Like inter-annotator agreement on the validation set with full chart review. So 2 expert cardiologists reviewing 40 cases is 0.8 to give you a sense of the difficulty of the task. So here it is. We do see some drop in performance. So we see that the average precision drops to about 0.82 from about 0.88. And AURC also sees a slight drop, but the model, all in all, generalizes really well, which we think is really promising, because it sort of tells us that we're capturing what we want to capture in terms of information. Awesome. So we found that this framework works really well for heart failure. I think it's very practical in terms of enabling biological, downstream clinical and biological research that can be done with these labels now that we have them. And on the left here, you're just seeing we go from positive predictive value of ICD code being 36% to our final definition being 81% on the validation set. And that's great. Now we have a better set of encounters that we can work with. And the next steps could actually be to apply this to clinical trial data. So Chris explained retrospective versus prospective studies. And I think this is a great example in which retrospective research can help accelerate prospective research. So clinical trials are really expensive. And we've been told by clinicians that a lot of time and money is spent on selecting participants in the clinical trials. So you could imagine this kind of model really speeding up patient selection. You could have the NLP model run on a full cohort of people, and then clinicians can review model predictions and select people easier and better and save money and time. And in this case, money and time impact human health, which is great. So that's the little vignette of heart failure. I'm running quite late, so I'm hopefully just going to give you a quick overview of what hopefully we've learned from this. I think this framework is able to identify incident disease diagnoses with quite few labels. So as few as 250 labeled reports is sufficient to get excellent performance, which is great for maximizing the impact of clinical time. Pre-training enables models to learn with fewer examples, and also the longer attention window makes a big impact on downstream ability. Great. Since I'm running over time, predictably, I will speed through the second half of my presentation, which is about extracting quantitative measurements from cardiac MRI reports. And the clinical lead on this is Julian Heimowich at MGH, who's wonderful. And so cardiac MRIs are a diagnostic modality that allows you to look at the structure and function of the heart and make diagnoses. And once again, the reports are complicated. So here you're seeing technique in yellow, machine in orange, function and hemodynamics in green, and structure in blue. And what we're interested in really are all of these numbers that are highlighted in green and blue. So going back to the deep phenotyping hypothesis, if you want to build new phenotypes, you need endpoints for those phenotypes. And these measurements are contained in the reports, but there's just not a table where you can like easily access them to compare that or to build a model from like MRI images to numbers, for example. So they're in the reports and we can get them, but that's really the task. And these measurements can also appear in many different formats, which makes heuristic approaches really ineffective and tedious. So over here, you're seeing the same measurement, right ventricular and diastolic volume. Maybe let's do the index because that's showing up better on the projector in yellow. And they occur in a bunch of formats. What's before them is different. What's after them is different. How they're laid out is different. And so if you wanted to craft like a regular expression to get all of these, that would be really painful. And it would make it even more painful if you had 21 measurements like we do that often would like intersect with each other. So the goal here is we like want to label very few of these because it's tedious, but we want to be able to extract all of these simultaneously and with high confidence. That's kind of the goal. And we can do that with the workflow that we've designed. And a nice part of that is Prancer, which is a customizable interface to collect annotations, thanks to Monica, who's in the audience, Ariel and David Sontag from the clinical ML group at MIT. And so this is just a nice interface for clinicians to go in and label the things that we care about, like you can kind of see highlighted. And then we're able to take these annotations and, all right, maybe not. We're able to take these annotations and start modeling with them. I'll speed through the study design. We have another cohort called EWOC, which is the Enterprise Warehouse of Cardiology, another Star Wars initialism. And we see about 9,000 people that have cardiac MRI reports, and we decide to label about 370 reports, one per individual. And that's sort of enough for the model development step. And we can also set up this measurement extraction as a token classification problem. So let's say you have this sentence, right ventricular ESV is 55.01 ml. What you can do is basically predict a label for each token in that sentence. And so ideally, you'll want to predict null for the rest of the sentence and RV ESV for 55.01. So you just want the number and you can set it up as a named entity recognition task, basically. And we also read some stuff about the way that numbers being represented affecting arithmetic performance with transformers. I won't get too much into that, but we tried a bunch of different representations of numbers to see what happened because it relates to the vocabulary of the model as well. Turns out it doesn't make too much of a difference, so I won't get into it. So here is just a pictorial representation of our workflow. We have a bunch of reports. We sample a few. A clinician goes in and labels in Prancer. We can create a data set. We fine-tune the transformer-based model for named entity recognition. And then, yay, we have a bunch of structured measurements that we can use for downstream research. Great. So once again, we see pretty excellent model performance across all the different architectures and the different numerical representation schemes. So what you're seeing here is macro averaged F1 scores. So F1 harmonic mean between precision and recall. We compute the F1 score. for each of the 21 measurements that we're extracting, and then we average across them. So you're kind of seeing how well can we extract all the measurements. And 95% confidence intervals in the brackets. So you see, they're all very, very close, all within error bars. But I guess numerically the best is just a standard BERT model with a simple numerical representation scheme, which gets you about 0.957 macro F1. And once again, we see that we need very few labels to achieve excellent performance. So even this, if you look at the y-axis on this graph, we're already starting at 0.92 macro F1. So even 50 labels gets you pretty far, like that's pretty good. And then with 150, you get in the neighborhood of about 0.95, which is sort of excellent and what we see for our full training set as well. And once again, this sort of like intermediate conclusion from this particular vignette, we can simultaneously extract 20 different measurements with just a single model, which is just really practical and helpful. And we only need a small number of labeled reports to do so. And finally, we find that for this particular task, clinical pre-training doesn't make a huge impact on performance. So perhaps that gets into the question of what we need for different tasks. To summarize my portion before I hand it back to Chris, I hope that I've demonstrated with these vignettes that we have an approach that needs few clinician labels, that is hopefully a reasonable amount of time. When we published this cardiac MRI paper, we jokingly called it "one clinician is all you need," in reference to attention is all you need, because Julian labeled all of these reports on night shift when he was working and had some free time. So that's pretty cool. It runs on a single GPU. It's practical because it uses Hugging Face. So when new models are developed, you can just switch in a new model and see how well the new model does on your data. And it works with the constraints that we have, that it's behind the firewall, it runs locally, all of that good stuff. Awesome. I'll hand it back to Chris to kind of wrap us up.
Great, thanks. And yeah, just in conclusion, hope we've convinced you all that electronic health record data present an invaluable opportunity to advance clinical research. However, as we discovered, these data are typically not sort of research ready. And so much of our work has been just getting the data into shape to be usable by downstream analyses and modeling efforts. And to do so, we've established what we think is a practical and effective natural language processing-based framework for overcoming these hurdles. And as Pulkit mentioned, we're not quite in the zero or few shot regime, but the amount of effort required by the clinicians is relatively minimal. And so we can focus on what we care most about, which is new ways of predicting and understanding disease risk. So thanks so much for your attention. And if you have any questions, happy to answer them.
Yeah, thanks
Maybe
for the talk.
Go ahead.
Oh, thanks. Yeah, thanks for the talk. I was wondering with the heart failure example, you said the medical codes weren't always great. Did you ever try kind of some maybe like clustering the embeddings or something to see if you could come up with a more granular or refined kind of medical code?
Yeah, we did not really try to learn a function of the codes, for example, or even try to identify our own set of codes to use for heart failure. At least we have for other outcomes. Our argument was that I think, as we mentioned, these particular codes are established by the EHR, I believe it is, or they're essentially, this is the approach that pretty much everyone takes in the field, is at least my understanding. And the precision of these codes is surprisingly bad. So one might take other approaches, but we found that working with text was appealing. One, we haven't really validated this, but it might be more portable than codes, depending on differences in how different hospital systems use billing codes, as well as contexts where codes just don't exist, potentially in like a clinical trial, for example, where you only have access to clinician notes and not other structured data.
Yeah. I guess that's kind of, I think definitely the text is super powerful. I meant more like using the text to define some kind of, stratification, or like the equivalent of what codes would be, but learned from like the text that you have.
I see. We are producing embeddings of a sort of the text, which is what we're feeding into the downstream classification model. We have not really played around with kind of relating those embeddings to codes. As Emily mentioned, there's some work where people actually produce sort of low dimensional, but like dense representations of codes themselves, and often in conjunction with text, but we haven't really worked with that.
Cool, thanks.
I think also we envision like the deployment of this model being on text itself. So inference runs really quickly, like microseconds. So you could imagine like some model of this kind being deployed within the EHR, and like folks have done really cool research, anything in cancer, where it's sort of like continually integrated. So you could imagine having a model that just like as text is generated, like keeps updating its prediction. So then you wouldn't really need structured data in that context. But I think that gets into like deployment issues, which as we know is kind of its own rabbit hole. So
thanks.
To Pulkit, thanks so much for both of your guys' presentation. But to Pulkit, on your second part of your presentation, where you talked about extracting the cardiac MRI measurements, you mentioned in your plot that you got like a 0.9 plus F1 score with only like 50 examples on your validation set of like 100 plus points. And so do you have a sense for like how much your validation set captures that full diversity of ways people could write stuff in those notes? Because in your first slide, it looked like there's like a million different ways people write this. So it seems like really good performance from only 50 data points.
Yeah, it's a really good point. So our test set has 100 labeled reports. So that's kind of the resolution that we're working with on like what is the actual applicability. I think what we saw with that project is that these models have so much flexibility that they're maybe even able to learn from the context of like one labeled report when a measurement happens. Like we see really obscure ways to write it. Like we had one example in the training set and then it correctly works in the test set. We even saw some stuff, honestly, where like just looking while doing sort of like manual review of model outputs, where there were like instances where I don't know if that was in the training data and we saw the model correctly identify it. So I think context is really powerful. And I think that's also why clinical pre-training doesn't seem to have a big impact, because just this like self-attention paradigm is so sufficient to sort of identify these measurements. We're also obviously really concerned with like, we're extracting the right thing. We don't want to like confuse two numbers because that's important. So we did stuff like, associating the measurements that we extract with non-clinical outcomes to make sure, like sanity check, that we're doing the right thing. And we see what we're meant to see. So we're hopeful that that works as it does.
Is it possible to do something like text ablation or something to find out like what are the critical elements that are really important? And is that something that then could provide guidance to clinicians, as in like, be sure to notate this? Like that's something that would take quite a while to spread, but like I'd imagine like one hospital at a time, like note this, be careful about these. Is that something that you can do with these models? Looking at like,
yeah, we have in previous iterations of this model done things like run inference one sentence at a time and see which sentence matters the most for prediction, or the reverse, where you like remove one sentence of a report and see what changes the prediction the most. This is kind of a funny task because the information is already in the report. So it's not as if we're sort of predicting, we're more like identifying things. So it ideally should say like heart failure or like medical words that amount to heart failure. But yeah, I think it's a really fascinating question. We've also sort of been able to do like attention-based exploration of what the model pays most attention to in the heart failure case. There's this little like CLS token that Emily explained, and you can see what the CLS token pays most attention to in the discharge summary input. It's obviously a very imprecise art rather than a science, but it looks like it's paying attention to things that it should, like shortness of breath and diuretic loop and things like this. So yeah, to the larger question of like, can we standardized notes to make them easier? There's probably even like structured stuff that we could standardize in EHRs to enable better research. But I think that's more like a policy and hospital question rather than a modeling question.
How much variability do you think there is between other diseases? Like for heart failure, you needed about 200 labels, but you could imagine there might be some diseases where it's more well-defined or even more amorphous. How much do you think that number shifts around?
Yeah, that's an excellent question. We've tried this approach with stroke recently on ongoing work, and stroke is way less amorphous than heart failure, so it works really easily. Something like 100 reports gets you like 0.98 performance rather than like 0.9. So I think heart failure definitely is on the spectrum of being amorphous. But I think when we're talking about more longitudinal or developing outcomes like brain health related ones, like dementia, for example, I think that would be a really interesting use case for like capturing variability. So maybe there isn't even like a binary yes, no dementia label. Maybe it's more like a spectrum of functioning or cognitive capacity. And I think it would be cool to see how well these methods capture that. So you could maybe predict like a continuous number rather than just a binary outcome.